Good morning, everybody. Okay, as a reminder, we're going to have our first midterm on Wednesday, and that was February 14th? 15th? Yeah, it's a week from today. 15. Okay, so on the exam, you are allowed one-third letter size formula sheet. Good? So you're going to take letter size, divide it into 3/3. 1/3, you're going to use it for the first exam, the second third for the second exam, and the third for the final exam. So you can write whatever formulas you want.
So would you be using the sheet as a continuation?
Yeah.
Okay.
Yeah, you're going to keep the sheet with you.
Right.
So you bring it again on the second exam, you bring it again in the final exam.
So by the end, we'll have a whole sheet.
Yes.
Gotcha. Okay. Just make sure everyone's
Is it just the front side?
What is it? Go ahead.
I think he just asked it.
Okay.
Is it just the front side?
Yeah.
We just gotta get all the rules. Let's see how we can bend them.
One side.
What if it's hard for us to divide by 3?
It's hard to divide by 3.
I'm just kidding.
Err on the safe side and divide by 4. Okay. You can also bring Laplace table. That doesn't count in the 1/3. So if you want the Laplace table, if you have a good copy of Laplace table, just bring it along if you need it. Okay, what is the exam going to have? We're going to have 3 problems. Anybody want to guess what the first problem going to be? Laplace. Laplace and its properties. Partial fraction expansion, etc. What is the second problem going to be?
Block diagram.
Okay, block diagram.
Rotational systems.
What is it?
Rotational systems.
More generic.
A mechanical circuit analysis.
A modeling. And since we are electrical, most of you are electrical engineers, we're going to have a circuit. Op-amp circuit. A circuit or op-amp circuit. Now the circuit might have a trick in it. So you might spend like 5 pages doing it, or you might figure it out and do it in a few lines.
Okay.
What is the second part of the third problem going to be? Block diagram reduction and signal flow. Make sense? So here, you guessed what the topic is going to be, so I didn't even have to tell you. Okay. Any questions on the material? Go ahead.
How do you recommend us preparing for it?
So read the notes, do the homework, solve as many problems as you can. I mean, we have homework, but that's really the minimum that you have to do. But the book has lots of good problems. They're very.
Question over here, sir.
Go ahead.
On the notes online, I noticed that 5, 6, and 7 don't appear to match what I was writing in class those days.
Okay.
And the block diagram and Mason's rule aren't in the posted notes anymore.
Okay, I'll look into them. Thanks. I mean, one thing that applies to this class and applies probably to any class. You might look at the notes or watch the lectures and say, okay, it's straightforward, I can do it. But it's another thing to try to do it yourself. Does that make sense? So even the notes, like look at the example and try to do it yourself. Make sure you can do it on your own. Because, you know, when you're studying, you can get help. You can go back and look at the notes. But on the exam, if you're stuck, there is no help. Make sense? So lots of things might appear very simple, and they are if you practice them. But if you don't, you're gonna find yourself struggling with them. Okay. So in the previous class, we started the discussion of second order system. And we said the transfer function of second order system that we're going to consider is going to have this format. Omega n squared over s squared plus 2 zeta omega n plus s plus omega n squared. We call this natural frequency. And we call this zeta the damping ratio. And we'll see why we call them these names. We said you have to always be careful when you have, if you see any system that's the second order, make sure it conforms to this format. If it's not, massage it, multiply it by a factor, take a constant out, till it is in this format. Okay. So what we're going to do, I mean, if you have, actually, let me ask you, if you have a second order system like this, and we want to study its behavior, what do you think the thing that's going to determine how this system is going to behave? Out of, like, guessing.
The damping ratio.
What else? What else? Like, if you were to study it, what is the first thing that will come to mind?
Poles.
What is it?
Poles?
The poles. Where the poles of this system are located, isn't it? Because, you know, this is second order. The poles might have different location depending on these parameters. And this is the approach we're going to take. We're going to look at these values, the zeta, omega n. We're going to see where the poles are going to be located. And based on each location, how the behavior is going to be. Make sense? Okay. So we know if we have a quadratic equation, as squared plus bs plus c equal to 0. If I want to find the roots of this equation, this is going to equal negative p plus or minus square root of b squared minus 4ac divided by 2a. So we're going to apply this to our denominator to find the roots. So if we have s squared plus 2 zeta omega n s plus omega n squared equal to 0, we're going to find the poles of this second order system. We're going to have S1 comma 2 equal to negative 2 zeta omega n plus or minus square root of 2 zeta omega n squared minus 4 times a, which is a 1, and c, which is omega n squared. All this divided by 2. So the poles of our system are going to be given by this formula. We can simplify this. This is equal to zeta omega n plus or minus square root of 4 zeta squared omega n squared minus 4 omega n squared divided by 2, which is equal to negative minus 2 zeta omega n square plus or minus. We can take the 4 and the omega n squared outside of the square root. So we're going to have plus or minus 2 omega n, and we're going to have a square root of zeta squared minus 1, and all this divided by 2. And we can write this as negative zeta omega n plus or minus omega n multiplied by square root of zeta squared minus 1. And this is the form that we want. Okay, so these are the poles of our second order system. They're given by negative zeta omega n plus or minus omega n multiplied by square root of zeta squared minus 1. Okay. So if you look at this, the location of these poles, what do you think is going to determine the nature of these poles?
The, whether or not whatever under the radical is positive.
Excellent. Which is going to be determined by this zeta here. Zeta, depending on the value of zeta, the roots are going to be either real or imaginary. So therefore, what we're going to do, we're going to look at what happens for each case of the value of zeta. So starting with zeta, we're going to look at what happens if zeta is equal to 0, what happens if zeta is less than 1, what happens if zeta is equal to 1, and what happens if zeta is greater than 1. What are the poles going to equal to if zeta is equal to 0?
Omega n if it's imaginary.
Uh,
Plus or minus.
Excellent. This term is going to cancel. It's going to be 0. 0 minus 1 is going to give me a j. So plus or minus j multiplied by omega n. So S1 comma 2 is going to equal to plus or minus j multiplied by omega n. And if I look at where these poles going to be, where are these poles going to be? On the j omega axis, yes. So we're going to have a pole here. We're going to have a pole here. This is j omega 1, negative j omega 1, omega n. Two poles are on the j omega axis. We're going to call this response undamped. Based on what we know, why are we calling it undamped?
Is it semi-stable?
No. We call zeta the damping ratio.
Oh, it's
If
zero.
zeta is 0, undamped, I mean, at least makes sense. We'll see later on why it is indeed undamped. Okay. The second case is what happens if zeta is less than 1? We're going to have S12 equal negative zeta omega n. And plus or minus j, excuse me, omega n square root of 1 minus zeta squared. Okay. If I have a square root of zeta squared minus 1, I can take a negative 1 as a common factor. So then I'm going to have zeta squared minus 1. I can take a negative 1. It's going to be negative 1 squared, negative multiplied by 1 minus zeta squared. Negative 1 is going to give me a j. And then I can write it as square root of 1 minus zeta squared. Zeta is less than 1. So this term is going to be real. Makes sense why we wrote it like this? Okay. So if I look at this case, where are my roots going to be, my poles? Negative zeta omega n plus j omega n square root of 1 minus zeta squared. Zeta is less than 1, so this term is going to be positive. Where are the roots going to be? They're going to be complex. Are they going to be right hand, left hand? Left hand. So we're going to have two roots that are going to be complex conjugate of each other. And the real part of them is zeta, negative zeta omega n. The imaginary part is omega n square root of 1 minus zeta squared. So these are complex conjugates. And we're going to call this case underdamped. Again, if it is zeta is a damping ratio less than 1, okay, we're going to call it underdamped. Let me ask you a question. Is it clear why when we have a complex root, we always have the conjugate of it? Why is it always when we have a root, the complex conjugate of it is also a root?
Because you're getting it from not, like, when you break it down in the quadratic formula, it's not perfectly, it always is going to have 2, right?
Why?
I don't know how to explain it. I just know where.
Yes, but I mean, all what you said is correct. But the reason why is because all the terms here are real. If these terms are real, the only way these will be real if the imaginary part cancels out.
Okay.
Does that make sense? If I have a root that is complex and I don't have the conjugate of it, what is it going to be? S minus a constant minus j a constant. And that will be the term that I'm going to have in my equation. Since I don't have, these terms are real. 2 zeta omega n is real, omega n squared is real. The only way they can be real if the complex part cancels each other. Does that make sense? So as long as we see a function with real constants, then all the roots are going to be complex conjugate. Make sense? Okay. The third case we're going to look at is what happens when zeta is equal to a 1. And when zeta is equal to a 1, the 1 squared minus 1 is going to equal to a 0. And the roots are going to be S12 is going to equal to negative zeta multiplied by omega n, which is equal to negative omega n. Where are we going to have the roots?
On the real side of the graph?
Excellent. On the real side. And how many roots are we going to have on the real axis? 2 roots. Both of these 2 roots are going to be on top of each other. So here we have two poles. And we're going to call this case critically damped. And finally, the last case is when we have zeta greater than 1. And in this case, we're going to have negative zeta omega n plus or minus omega n square root of zeta squared minus 1. Where are the roots going to be? Zeta squared is greater than 1, so this is going to be real. So it's going to be a real plus or minus a real value. Where are the roots going to be? They're going to be on the real axis. And they're going to have two different locations. one that's coming from adding omega n square root of zeta squared minus 1, and one from subtracting it. And this case, we're going to call it overdamped. Is that clear, everybody? So 4 cases, zeta equals 0. We're going to have our roots on the j omega axis. How does the response of this system, who remembers this from the lab yesterday? Excellent. If we applied a step, we're going to have a step that goes up oscillating. But if I apply a sinusoidal signal to this system that has omega n, then it's going to grow out of control. It's going to become unstable. So we call this system marginally stable. Okay, the second case is when zeta is less than 1. We're going to have 2 poles in the left-hand side. We're going to have real part and imaginary part. Zeta equal 1, we're going to have 2 poles on top of each other on the real axis. Zeta greater than 1, we're going to have 2 poles that are on the real axis. We call first one undamped, underdamped, critically damped, overdamped. Okay. So let's look at the response of the system and explain why we're calling this underdamped, why we're calling this critically damped, why we're calling this overdamped. So to do that, we're going to come to our system and we're going to look at the response of the system when we're applying a step. So similar to how we've done with the first order system, we're going to come here and apply R of S that is equal to 1 over S, and we're going to look at C of S. Apparently, since zeta determines the location of the poles, when we look at the response of the system, we have to break it depending on the value of zeta. So we're going to look at different cases depending on the value of zeta and look at how the response looks like. So starting with the first case, when zeta is greater than 1, we call this overdamped. And in this case, we have 2 poles on the real axis. So I have a pole, I have another pole, and we're going to call this pole negative A, negative B. These are my poles of the system. So if I look at C of S, the response of the system, 1 over S multiplied by omega n squared divided by S plus A multiplied by S plus B. So since these 2 poles are going to be real, I'm just going to say they happen to be A and B. So I'm going to be able to write the denominator as S plus A multiplied by S plus B, because we assume zeta is greater than 1. So we know the poles are going to be real on the real axis. Okay. Does that make sense, everybody? So similar to what we've done when we calculated the output, we're going to do partial fraction expansion. This is going to expand as A over S plus B over S plus A plus C divided by S plus B. And therefore, we can write this as equal to, let's calculate the value of A. What is the value of A equal to?
Omega n squared over AB.
Excellent. Omega n squared over A multiplied by B. Agree? But what is A multiplied by B equal to?
That's omega n
Squared.
squared.
Agree?
Not agree.
Everybody? I mean, this, remember, this is 1 over s squared plus 2 zeta omega n s plus omega n squared. When I multiply this equation, A multiplied by B is equal to omega n squared. So A multiplied by B is equal to omega n squared. Which is equal to a 1. We cannot determine the value of B and C because it's going to depend on the small a, small b. So we're going to keep it in terms of B and C. So we can calculate the inverse Laplace, and we're going to get C of t, that is equal to a 1 plus B multiplied by e to negative a multiplied by t plus C multiplied by e negative b multiplied by t multiplied by u of t. Agree? The inverse of these terms here. How do you think this response is going to look like? If we applied a unit step, so this is 1, this is my input, this is r of t. How is the response going to look like? It's going to start at 0 and it's going to go all the way to 1. So this is our C of t. Together? Make sense? How is it 0 at t equal to 0? I mean, at t equal to 0, this is going to equal 1 plus b plus c. How is it going to equal to a 0?
Because B and C had the same denominator, and so if they would have the same constants, and so having 0 e to the 0 is going to be 1. And then cancel.
Is it because of the unit step? You've multiplied, you're starting at 0 to 1? Everything before that's nothing.
Yes, but my question is, when I plotted this curve, this C of t, which is here, but if I plug in 0, when t is equal to 0, I'm going to get 1 plus b plus c. How is it 0?
Because of U of t.
Because b and c are going to be such that equal negative 1 at t equal to 0. b plus c are going to equal negative 1. Does that make sense? So even though we have them as b plus c, b can be positive or negative, c can be positive or negative. So we can get a 0. Did I make you more confusing than I should have? Just keep in mind, b and c are constant that can be positive or negative. So it is possible. Like at first glance, you look at this and say, oh, it's 1 plus b plus c. This must not be a 0. But no, b and c are adding them together is going to equal negative 1. Is going to be equal to a 0 at 0. Okay. What did we call this response? We called it overdamped. Zeta greater than 1, we called it overdamped. Okay. The second case, is when zeta is equal to a 1, and this is the critically damped, and this is the case where we have two poles at same location. So C of S is going to equal to omega n squared divided by S squared plus 2 zeta omega n multiplied by S plus omega n squared multiplied by 1 over S. And we can write this as omega n squared divided by S plus omega n squared multiplied by 1 over S, because zeta is equal to 1. Together? S plus omega n over all squared is equal to S squared plus 2 omega n S plus omega n squared. So I can write this in this form. Okay. Again, we're going to do partial fraction expansion. This is going to expand as 1 over S minus 1 over S plus omega n minus omega n divided by S plus omega n over all squared. Okay. We can take the inverse Laplace of this expression. And that is going to equal to a 1 minus e to negative omega n multiplied by t minus omega n multiplied by t e to negative omega n multiplied by t u of t. Where did I get this one from? Laplace tables. This is a typical form. We can easily find the inverse Laplace form. If I have omega n over s squared plus omega n squared is going to equal negative omega is going to equal omega n t e to negative omega n multiplied by t. Okay. So we're going to do the same thing. We're going to come here and plot the response for a step, and the response for a step is going to look something like this. Critically damped. When t is 0, same thing. This is going to 1 minus 1. This is going to be a 0, and is going to grow to a 1. Okay. Now if I look at this response, and I look at the response of the overdamped, what do I notice? They have the same shape at least. How do I differentiate one from the other? The slope, yes, and at the rate at which they So if I have multiple curves like this, if I have one curve, I'm not going to be able to tell whether it is critically damped or overdamped. But if I tell you these curves belong to a critically damped and overdamped, which one is going to be the critically damped? The one, the fastest. Does that make sense? The one that is the fastest. So zeta, as we reduce zeta, the system is going to get faster, 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 till we have zeta that is equal to a 1. Make sense? So this is zeta equal to a 1. This zeta, this zeta, this zeta, this zeta, zeta, this zeta is less than this, less than this. So as zeta increases, we have more overdamping, and therefore it's going to go slower. Is that clear? Make sense? Okay. The next case we're going to look at is the case when zeta is less than 1. And we call this underdamped. And in this case, we have two complex poles. Now, as we will see, this is the most interesting response of all the responses. All the responses that we've seen so far, if you were to describe them with one word, what is that word going to be? Boring. Excellent. The first order is boring. Second order, if it is overdamped, critically damped, boring. And that's why the most interesting is the one of the underdamped response. So if we have an underdamped response, we have two poles, negative zeta omega n plus or minus j omega n square root of 1 minus zeta squared. What we're going to do, first of all, we're going to take this term, we're going to define it and call it sigma. And this represents attenuation. And we're going to take this term, omega n, multiplied by square root of 1 minus zeta, and we're going to call it omega d. And this is damped natural frequency. So we're going to define sigma, which is going to equal zeta omega n. We're going to define omega d, that is equal omega n square root of 1 minus zeta squared. Okay. Now let's look at the response of the system.
Does the attenuation include the negative, or is it just zeta omega n?
Just zeta omega n. Okay. So let's look at C of S going to equal omega n squared divided by S squared plus 2 zeta omega n multiplied by S plus omega n squared multiplied by 1 over S. Now if we expand this, this will expand as the following. A over S plus BS plus C divided by S squared plus 2 zeta omega n multiplied by S plus omega n squared. How did I know it expands like this? I looked at, go ahead. I looked at the tables for partial fraction expansion, how to expand a term that like this. They told me you can expand it like this. Make sense? And like you could have expanded this as just a constant here. Then when you try to find the values, you're going to realize a constant here will not work. Does that make sense? Because you're going to have this term equal to this term. If I have just a constant, it will not work. If I had just b multiplied by s, and then try to verify that this is equal to this, it will not work. You realize I have to have b multiplied by s plus c to be able to make this side of the equation equal this side. Does that make sense, everybody? So I don't want somebody looking at this and say, oh, how did he know it's bs plus c? What I'm saying is, you can always look at how to expand, and I think I have some formulas here that you can look at if you're interested, the expansion of a second order complex roots. But for the time being, we're going to verify, indeed, I can write it as such, because I'm going to find the values for b and c and a. Make sense? Okay. So looking at, and we're going to see why we're expanding it also like this. It will become clear. So I'm going to unify the denominator. This is going to equal to s multiplied by s squared plus 2 zeta omega n s plus omega n squared. What is the denominator? The numerator going to equal to a multiplied by s squared plus 2 zeta omega n multiplied by a multiplied by s plus a multiplied by omega n squared plus b multiplied by s squared plus c multiplied by s. Agree? If we add these two expressions together, a is going to multiply by this, and this is going to multiply by s. Now this has to equal to this. So therefore, if I put the terms together, omega n squared that I have on the left side, omega n squared, the numerator, has to equal to, I have s squared multiplied by a term, I have a term that multiplies s, and I have a constant. So if I put the terms together, what do I'm going to have here? Anybody knows what I'm doing? A plus b. Yes, it's going to multiply s squared. And then if I look at the s, I'm going to have 2 zeta omega n a, and I'm going to have c. And then I'm going to have a multiplied by omega n squared. Okay. So therefore, I'm going to write a plus b, and I'm going to have 2 zeta omega n, omega sub n. So keep that in mind. N is not, omega is a subscript. Sub n plus c, and then I have omega n squared multiplied by a. So this term and this term together are going to give me this, this, and this. Going to give me this, and this is going to give me this. Okay. So left side must equal to the right side. What is A going to equal to? This side equals to this side. Here I have only omega n squared. Okay, I'm going to come to the constant here. I have a omega n squared. What does a have to equal to? 1. Okay. What does b has to equal to? -1. What does c has to equal to?
-2. So the negative.
Everybody agrees? -2 zeta omega n multiplied by a, but a is equal to a 1. Okay, great. So therefore, what we establish is the following. C of s can be written as equal to 1 over s minus s plus 2 zeta omega n divided by s squared plus 2 zeta omega n s plus omega n squared. Agree? We have negative, so I can just multiply the whole thing by negative sign. Okay. I can write this as 1 over s minus s plus zeta omega n divided by s squared plus 2 zeta omega n s plus omega n squared minus zeta omega n divided by s squared plus 2 zeta omega n s plus omega n squared. Agree? I have 2 zeta omega n. I just split them into two terms. Okay. Now we're going to do, I'm going to come to this term here, both of these, and I'm going to complete the square. So I'm going to come here, and I'm going to say I have s squared plus 2 zeta omega n s plus omega n squared. How do we complete the square? We're going to take this coefficient divided by 2, add it, and subtract it. So we're going to add zeta, square it, and then add it and subtract it. So we're going to add zeta squared omega n squared, and we're going to subtract zeta squared omega n squared. So nothing changed to this equation. We added and we subtracted, we still have the same expression. So then what we can do, we can take this term, and this term, and this is going to give me s plus zeta omega n over all squared. And then I'm going to be left with plus omega n squared minus zeta squared omega n squared. And we'll see why we're doing all this. So what I like to do, I like to take this denominator, I want to write it like this. And we've seen it can be written like this. I can also write this as s plus zeta omega n squared plus omega n multiplied by square root of 1. That's right. Plus omega n squared multiplied by 1 minus zeta squared which we can write as S plus zeta omega n squared plus omega n square root of 1 minus zeta squared over all squared. Agree? Okay, we'll see why we're doing this. Okay, so going back to our expression, we can write this as 1 over s minus s plus zeta multiplied by omega n. And now I'm going to replace the denominator with the new expression that we got, which is s plus zeta omega n squared plus omega n square root of 1 minus zeta squared over all squared. And then minus zeta omega n divided by s plus zeta omega n squared plus omega n square root of 1 minus zeta squared. Okay. Now just to simplify the notation, I'm going to write this as 1 over s minus s plus sigma divided by s plus sigma squared plus omega d squared minus sigma divided by s plus sigma squared plus omega d squared. Remember, we defined zeta omega n as sigma, and we defined omega n square root of 1 minus zeta squared as omega d. So instead of writing all these terms, we can just use the sigma to represent zeta omega n and omega t to represent omega n square root of 1 minus zeta squared. Together? Okay. What do we do next? We're going to go to the tables and get the expression for the inverse Laplace of this expression. And that is going to equal to 1 minus e to negative sigma multiplied by t multiplied by cosine omega d multiplied by t plus sigma over omega t sine omega d multiplied by t. Together? So using the tables, we can get the inverse Laplace of the expression, which is going to be given by the expression that we have here. Now, if I look at this expression, how do you think this response is going to look like?
Sinusoidal?
It's going to oscillate. I mean, you can see there's going to be oscillation because I have a sine and a cosine. But these oscillations are multiplied by an exponential term that's going to get smaller and smaller and smaller. Does that make sense? So as t increases, the oscillation is going to die out. When t is 0, they're going to have the major impact. And then as t increases, the oscillation will die out. So therefore, if I were to plot the response of this system, I might get a response that looks like this. I might get a response that looks like this. I might get a response that looks like this. All these are examples of an underdamped response. Together? Now, if I were to add to this the critically damped, it's going to look something like this. What is it we noticed about the underdamped compared to the critically damped?
It shoots up quick, but it overshoots.
It's faster. Yes, it is faster. Remember, the overdamped is even slower than the critically damped. So critically damped, the underdamped is faster than the critically damped is faster than the overdamped. But the underdamped is going to have this oscillation in it. Okay. So let's look at MATLAB and generate a plot of all these responses. So if I run MATLAB, with different values of zeta and generate the step response. So let's compare when zeta is equal to 1, when zeta is greater than 1, what did we notice? Zeta equal to 1 is the fastest, which is consistent. And then if I look at the response as we vary zeta, can you see the different colors? You can, zeta equal to 1 is, let me highlight it here. Actually, let me do this. Oh, we're still outside the border of the page. Okay, good. Okay. So if you look at the second order response, and I'm going to highlight the extreme values so you can see them. So when zeta is equal to a 1, it's going to give me, I'm going to have this response here. And zeta equal to 0.9, that is the one next to it. 0.8, 0.7, 0.6, 0.5, 0.5, all the way to 0.1. Make sense? What color should we use? So this one corresponds to zeta equal to 0.1. This is zeta equal to 1. Sounds good? So what do we notice? When zeta is 1, the critically damped, underdamped is faster than the critically damped. And as zeta is decreased, what happens to the overshoot? I mean, we're going to call this overshoot. What happens? We're going to have more overshoot. Makes sense? And more oscillation. All the way when zeta is equal to 0, what are we going to have? This oscillation here. Okay. Okay. So this is the expression that we got for the underdamped. Now we have a cosine and a sine. I can take this expression and combine it together in another form. So similar to what we've done in the first lab. So let's look at, just do an example. And we're going to show that second order response C of t equal to 1 minus e to negative zeta omega nt multiplied by 1 cosine omega dt plus zeta over square root of 1 minus zeta squared sine omega d multiplied by t. Which is the expression that we just derived for the response of the underdamped response. I'm going to show that it can be written as C of t equal to 1 minus e to negative zeta omega n multiplied by t divided by square root of 1 minus zeta squared multiplied by cosine omega dt minus phi. Where did we see something similar to this? In the first lab, remember the lab, we have the two sinusoids, and we're going to show that it can be written as a sine with a phase. Okay. So we're going to use the identity that tells us if I have a cosine omega t plus b sine omega t, I can write this as r cosine omega t minus phi, where r is equal to the square root of a squared plus b squared, and phi equal to tan inverse b over a. What are my a and b? So this is my a, and this is my b. So I can take this a, which is a 1 cosine, plus b sine, and use this expression, this identity, to write it as a single cosine. Okay, so r is going to equal the square root of a squared plus b squared, which is going to equal the square root of 1 plus zeta over square root of 1 minus zeta squared over all squared, which is going to equal the square root of 1 plus zeta squared over 1 minus zeta squared. Which is going to equal the square root of 1 minus zeta squared, 1 minus zeta squared plus zeta squared, which is going to equal to the square root of 1 over 1 minus zeta squared, which is equal to 1 over square root of 1 minus zeta squared. And phi is going to equal tan inverse b over a, and b was z divided by square root of 1 minus zeta squared divided by 1, which is going to equal tan inverse of zeta divided by square root of 1 minus zeta squared. Make sense? So therefore, R is this here, and phi is given by the tan inverse of zeta over square root of 1 minus zeta squared. So we might see the underdamped response in either one of these two forms. But the point is, both of these forms are the same. So I can see the response given by this expression here, or I can see the response given by the expression above it. Both of these are identical. Okay. Any questions? Okay, the last thing we're going to look at today is the representation of poles in the S-plane for the case when the response is underdamped. So the poles location when the system is underdamped are given by S1, 2, that is equal to negative sigma plus or minus j omega d, where sigma is equal to zeta omega n, and omega d is equal to omega n square root of 1 minus zeta squared. So what I want to do is I want to see how the poles are represented in the S domain, and I want to be able to look at the pole location and know what the value of zeta and omega n is. So if I come to my S domain, if I have a pole, what is this value here going to be? Sigma. What is this value here? Omega d. Okay. I can calculate the length of this vector here. What is the length of this vector? Sigma squared plus omega d squared, which is going to equal to the square root of zeta omega n squared plus omega n squared multiplied by 1 minus zeta squared, which is going to equal to if I square it, zeta omega n squared is going to cancel with the omega n zeta squared. So I'm going to just have the square root of omega n squared, which is equal to omega n. So the length of this vector is equal to omega n. What was omega n? Anybody remembers what omega n is? The natural frequency? Okay, so next, let's look at this angle here. We're going to call it theta. And let's calculate the cosine of this angle. What is cosine of theta going to equal to? Omega n, yes. Yes. Which is equal to zeta multiplied by omega n divided by omega n, which is equal to a zeta. So what does that mean? If I have poles and I can move them around, what happens when I'm at this location? What is theta going to equal to? 0. What is zeta going to equal to? 1. Because the cosine of theta is 0. If I increase theta, what's going to happen to zeta? It's going to get smaller, smaller, smaller. All the way, when I go all the way here, theta is 90 degrees. What is theta going to equal to? 0. Make sense? So I can look, by looking at the poles location, I can know what zeta is equal to. The bigger the angle, the smaller the zeta. Is that clear? Okay. So this is in the extreme cases. So when zeta approaches 0, and when zeta approaches 1, theta is going to equal pi over 2, and theta is going to equal to a 0. Together? Why did I not write zeta equals 0 and zeta equal to 1? What is it?
Isn't that what we're trying to find?
No, but why did I not write this as zeta equal to a 1? I wrote when zeta approaches a 1. No, I could have theta equal to 0. The reason is the following. Because I'm considering the underdamped response. Make sense? Underdamped response. Underdamped response assumes zeta is between 0 and 1. So I cannot go and say, oh, when zeta is equal to 1, it's not underdamped anymore. Make sense? Zeta can't be 0.99999 till infinity nines. It's still underdamped. But once it's at 1, it's a different. We did not do the derivation for the case when zeta is equal to 1. We did it for the case when zeta is between 0 and 1. Okay. And again, in general, so between the two, we're going to have something that looks like this. This is theta, and cosine theta is going to equal to zeta. Sounds good? Okay, thank you, everybody. Just stay. I'm going to take attendance because I feel like lots of people are missing. So if you're watching this lecture, I want you to know that we took attendance, and they're going to be marked as not in class.